are enrolled in. I actually thought of replacing this guy with a figure, but I thought that wouldn't be right. His first name is Sadi, and his last name is... That's not a great name. Carnot. Sadi Carnot. And he should have invited some former students of mine. Okay, great laws of science. Okay, no matter whose picture I put up there, what would you say when I asked you the great laws of science? The greatest law of science. The second law. Okay, she remembers. Okay, the second law of thermodynamics. Carnot was a French engineer, died at an early age, but before he died, he made some key observations about the working of the steam engine, and he was obsessed with making them more efficient. Watt, the Englishman, had developed the steam engine, but the French engineers were going to make it more efficient. And he made some key contributions. He was a little bit run off course by the prevailing idea of caloric theory, which we talked about earlier in class. And it was his posthumous papers that were found by another great thermodynamicist corrected some errors and outfell the second law. So what's the second law? Entropy increases in the universe as time goes on. Okay, again, I'm trying to focus on how these laws, what these laws say about complexity and time. Okay, let's move to the next slide, Michael. Start focusing in on this. Here's an interpretation of Isaac Newton's laws of motion that I prefer to the mathematical equations. We know Newton developed the calculus in order to explain the idea of bodies at rest and bodies in motion. This interpretation of Newton's laws came about 1,000 years before Newton, the Rubaiyat of Omar Khayyam, the great tent maker. The moving finger writes, and having writ moves on. Nor all your piety nor wit shall lure it back to cancel half a line, nor all your tears wash out a word of it. And that inverted pole they call the sky, whereunder, crawling, cooped, we live and die. Lift not your hands to it for help, for it is impotently moved as you or I. With earth's first clay they did the last man knead, and there the last harvest sowed the seed. And the first morning of creation wrote what the last dawn of reckoning shall read. Yesterday, this day's madness did prepare. Tomorrow's silence, triumph, or despair. Drink, for you know not whence you came, nor why. Drink, for you know not why you grow, nor where. And above that, there's a clockwork. Newton's laws have been interpreted correctly to say that if you know all the positions of everything in your system at a certain time and all the forces on them, you can integrate your way away to get position, velocity, acceleration of every particle for all future times and all past times. In other words, the success of Newton's laws brought people to the idea that the universe operated like a giant clockwork that some creator had set in motion at one point and then let go. And everything was exactly determined. That's the beauty of and the vein of Newton's equations. Everything is exactly determined from initial conditions, going backward or forward. In other words, there's a reversibility to time. The laws work in both directions equally. There's no specialness about the past or the future. So, let's move on to the next one, Sadi Carnot. The second law is often called the arrow of time because we see that entropy increases in all real processes. And so if we were to watch a motion picture and someone said, this may be playing backwards or forwards, you tell me, you could watch for subtle hints as the motion picture went on about certain types of events and figure out if it was in fact being played forward or reverse. Okay, the classic example, of course, is a person is in a swimming pool. All of a sudden, water goes all over the place, and they're back on the diving board. Backwards. It's backwards, okay? The splashing of water all over the place when the impact, the kinetic energy converted into basically random thermal energy. Eventually, the pool warms up a couple of fractions of a degree. Okay, so Carnot's principle took the reversibility of Newton's picture and smash it to bits. He's, in fact, this business of the arrow of time has been the title of many books on thermodynamics and many books about the process of life, because interestingly enough, life can only occur if everything is just so highly organized system of cells and organs and organelles, and at first it appears to violate the second law. And for a long time that caused people real problems. I'll say more about that in a minute. But for now, we have taken a directionless time or a forward-backward equivalence, and we have changed it dramatically to say the forward direction of time is different from the backward in the sense that entropy increases. What is entropy? Disorder. And so it implies a breaking down into more and more fundamental bits. From our simplest examples of the second law, heat flows from a hot body to a cold body. And so the entropy death of the universe has been predicted where all the hot spots have been leveled down and their heat has flown into the colder spots, and we have sort of a lukewarm, uninteresting mess on our hands, and that's the end. Again, that is provided, certainly Carnot has provided some important insights that did allow us to, for example, improve the efficiency of the system. But it leaves us with some questions about, is this the correct picture of time? Now we'll get back to Charles Darwin on the next slide. Oops, what happened to Charles? Connected by music, I guess that's. Let's see if we can go back one step. Okay, no, okay, Charles comes after the video. These two videos are to give you a quick lesson in what entropy is at the molecular level. So, play away, Mike. Notice there's a clock in the picture. Okay, can someone sum that up in 30 words or less?
It was a spontaneous process, and then somehow it was a non-spontaneous process, and it wouldn't happen to the first stage.
Okay, the first process was spontaneous. The normal direction of time is for 8 balls to distribute themselves equally into the 2 containers. This is a very allegorical. This is a simple sort of way to show the idea. As we said about heat before, heat flows from the hot body to a cold body. The side that has a lot and the side that has none even out over time. And then the second process was something that will never happen, the reverse process. Will that never happen? Will 8 gas molecules never congregate on one side of a container?
You could put work in. Energy.
Yeah.
Go back to the same side.
Right? But, well, let's watch a second movie, and I'll ask you a different question. That's right, you can put work in, and you can take control over the situation. The next concept is a little bit tricky, so watch very closely. So tricky, I had to reduce the number of balls from 8 to 4, so you can see if you can figure out what's going on in this. Okay, who's going to explain this one to us? Should we watch it again?
It was getting.
Okay, actually, Michael?
I was saying they kept rewinding and showing it getting disordered in a different way. Like,
Right.
they're showing all different
Okay.
combinations of what could happen.
That's a key insight, okay? They're showing different ways to get certain kinds of results. And the pictures at the top, I'm sorry, the quality of the video degraded when I switched from one format to another. The pictures at the top kind of recapture the different ways you can get a result that's kind of the same. This last one is, what is the result of this last one? Equilibrium, 2 and 2, okay, 2 on each side. But if you watch closely, the colors of the two paired up in all possible ways, and there were 6 ways you can get 2 and 2. There were fewer ways you could get 3 and 1. How many ways can you get 3 and 1? 4. That 1 can be either of any of the 4 colors. And the first one was 4 and 0. There's only one way to get that. We had one way to get 4, 0, 4 ways to get 3, 1, and 6 ways to get 2, 2. So guess what's the equilibrium situation? The next slide captures this insight in the tombstone of Ludwig von Boltzmann, who worked out a lot of this stuff right around the turn of the 20th century. And his equation is on his gravestone. S equals K log W. The entropy is equal to Boltzmann's constant times the log of the number of ways you can get a certain result. And the highest entropy, obviously from the equation, is the one that corresponds to the most ways. So going back to the earlier video of 8 balls and 0, and the statement that this is impossible, it's not really impossible, it's just impossible in a statistical sense. All the other ways of distributing 8 balls into 2 containers are more probable than 8 and 0. And if you change from 8 and 0 to Avogadro's number of molecules, how many molecules is that? A mole, yeah, how many is that? 10 to the 23rd.